class. Good morning, good afternoon, good evening. So welcome sa ato ang next topic for our pre-elective mathematical modeling with MATLAB applications. So previously we discussed on one mathematical model that is used in solving problems, interesting problems in economics and also in business kay sa katong BAS model. So we know sa iyang purpose sa katong BAS model, that is technically to forecast and do prediction on if ang imong product ba nga gi-introduce would be appreciated or be i-consume ba sa imong mga customers or imong consumers, if it will be well received ba siya, okay? And ang imong product ba sustain ba siya, or will it just die out eventually or at a earlier stage sa iyahang pag-introduce. Okay. This time, this is similar po actually siya sa kanang concept. We also do predictions here because that's technically how mathematical modeling works. We somehow want to forecast what will happen in the future given this initial condition. Okay. Now, for this case, we'll be talking about infectious diseases because I believe this is very relevant and timely, especially we are now experiencing this unprecedented event on coronavirus COVID-19, and people are going crazy about it, and some are afraid, and some are even doubtful. Will we be able to overcome this? Hopefully in the future. But what about our model, the science behind it? What does the science or the mathematical models that we have say about the future of this event? Will it die out? Will it continue? Or if it will die out in the near future, when? So, and what are some precautionary and preventive measures that we can do so that we can help also in para makakontribute nga mawala na gini siya ang pandemic, because it's really causing a lot of harm, not just on our mental, on our physical, but also sa atong economic. Okay? So we'll be talking about here mathematical modeling of infectious diseases, because there are actually many infectious diseases that we are facing in this world, not just COVID-19. Even in the past, we've experienced a lot of infectious diseases already, pandemics, like atong Spanish flu, the Black Death. You can search it on the net. Those were some of those deadly pandemics that we experienced in the past. And for this session, we'll just focus on some specific infectious diseases, especially COVID-19. So the things nga kanang mag-study ka sa diseases, how it originates, how it passes through other people, other hosts, and how it can be prevented. These are encapsulated into just one term. One study. You have the epidemiology. So why do we study epidemiology, by the way? So epidemiology is it studies and identifies this one. It studies and identifies. Let me do this. Okay, honest. So epidemiology studies and identifies. It studies and identifies characteristics of a group population. Studyhan niya ang as a whole ba iyang tanawon, not on the individual part. So iyang tanawon is a collective, say the community or with a whole city or even a whole country. So it actually groups population with similar characteristics such as the same sex, the same age, the same size, the same ethnicity maybe, etc. And ignoring also the uniqueness of individual members, because let's say mo siya og study ka sa physics, if you want to study the dynamics of let's say water flow, then we just have to consider the characteristic of the group of these water molecules. We are not concerned on studying the individual water molecule, but the whole system itself. This is like this for sa epidemiology. Also, it determines whether the groupings tells us something more than observing it individually exactly. Because kani siya masulod din siya sa usa ka term na what we call actually complex system. Na ang individual behavior is not so useful siya if tanaw lang ka sa iyang individual, but mas importante or mas daghang makuha ang information if we just look at the groupings unsa ang iyang behavior if mag-group siya together. Kasi mo na siya sa mga kasi we are all composed of different atoms and we are composed of the same atoms and molecules, say the same electron, the same proton, but given the same protons, the same electrons, if we group mo siya together, lahi ang ihang mamugawas na property. Could be mahimo siyang water, could be mahimo siyang oil, but those are composed of the same atoms, right? The same siya nga, have the same fundamental particle. You have the proton, you have the neutron, the electrons. It's like that. And so, this epidemiology, it aims to describe, analyze, or understand patterns of diseases in such groups. Okay, and also understands the dynamics of infections because it occurs at multiple scales. We have micro. Micro is from within the body of a certain organism, and we also have meso, meaning the pathogen the pathogen is present in each individual and it transfers from individual to individual. And we also have macro, meaning from group to group, from community to community. In our case, we'll just focus on the meso because mawala siya ang ato ang ginatanaw when it comes to this yung sa pag-spread sa imuhang say coronavirus from person to person, how fast and by let's say given a certain amount of time, how many people now will be infected by that virus. And of course, if we want to study and do forecasting on this, then we have to translate it in mathematical terms because doing mathematical modeling would give us an ease in manipulating data, and then it will give us sensible or will make sense ang imong result because if we have this number and we can do forecasting, pila man gid ang number up to a specific amount of time, given the initial conditions of the number of infections and the number of susceptibles and the number of total population initially at hand. So we aim to understand the salient features of infection dynamics, and that is we do forecast. It comes to the outcome of the disease in communities from the changes in demographics, okay, community structure, and disease characteristics and control. Because importante man ang result aning mathematical modeling sa epidemiology because it will paangin siya, makahatag siyang impact as to kung sa'y dapat mahatong sa government. It comes to sa iyahang policy. Na siya impact sa policy ba? All for the cause na ang iyang main na cause ani is to really help people, right? Help people not to get infected and also to help the hospitals kay basi ma-overwhelm ang hospitals sa mga patients, right? And we don't want that. So, ano siya ang purpose ani to have the disease characteristics and somehow sa may control na to dapat. Then we also want to understand the competing risk of death from diseases, especially kaning coronavirus. This is actually fatal. Yang severity ano niya ba? Yang fatality is taas compared to just normal flu. Then we also want to limit the extent of infection through some form of control. Maybe if we do vaccination, yes, vaccine is very important and crucial. But for now, wala pa man tayo vaccine. We're just waiting for other developed countries na ma-release na nila. Hopefully, by early next year or in the second quarter next year. Also, we can do quarantine measures, which is what we are doing right now. Quarantine measures. So this is what we are doing right now, quarantine measures, mga ECQ, we have GCQ, also lockdown. So, ang purpose niya is para i-limit naman, di ba, ang interaction between the infected individual and the susceptible katong wala pa na-infect. We don't want that to happen. That's why nataan ng mga measures. And we also do social distancing when we are in the mall or we are in any public places. This is very crucial also. Maintain, say, 2 meter distance. Calling animals, yeah, it could be. Possible man po ang animals kay, well, napay wala gyud proven nga study, but it could be nga ang animal pwede po siya mahimong carrier sa yung coronavirus, especially the dogs. And also, this is very important, we do contact tracing. Yes. Contact. Okay. Importante ka siya. Pulisod ka siya buhaton. Pero, dapat na ay concrete plan ang government when it comes to contact tracing and dapat speedy and immediate na siya dapat. Okay? Okay. At least ma-warn man na to ang ibang people. No? We have these infected people, so we have to isolate them. Okay? If not, then maka-worsen na noon siya sa imuhang problem. That's why importante kayo siya ang contact tracing. So what we are going to do here is we have a real system. So in this case, not a real system. Say coronavirus data, and we make a model. So how do we make a model? We look at the characteristic of the virus, how this virus is able to transmit other people, and what is the rate of infection, how severe or how fatal is the disease, okay? And then from that, we model the system by constructing theories, or we can perform simulations, okay? Or pwede po sa kanina route, lahi po siya from the real system, we do diretso ka experiment, okay? Experiment. And from the experiment, nakakuha ang experimental results. And then from that result, imo siyang i-validate sa imuhang tanawon sa model. Imo i-compare po nimo diri sa theoretical. Okay? So, duha man nga case ang mag-model ka. So, duha ka branch. It could be simulation and then construct approximate theories. And make theoretical predictions. And i-compare nimo siya. So, from that simulation results, again, pwede mo siya i-compare sa results sa katong from the experiment, and then also you compare that one to the theory mo siya i-validate. So when we do modeling, actually one cannot do away with the other. So we have mathematical, and we can also do the simulation. Okay, mag-uyog gini siya, importante man siya. Okay. We do simulation para paspas ang imong computation. Okay? And then, para paspas ang computation, then we can do some validation sa mga mathematical formulation. And siya all from the data. Okay? This is real data. From the real data. Then, from the simulation and mathematical formulation, you go back sa mga real data. What does the real data has to say sa imong sakto ba imong theory, imong model nga gigamit? You always go back to the real data. If not, then you have to design again and reformulate or improve your model. So, actually, daghan na nagbuhat aning the mathematical epidemiology way back in 1760 by Bernoulli. So, gibuhat ni Bernoulli is he formulated and solved a model for smallpox. Smallpox is a very deadly po siya disease. Especially sa una, wala pa vaccine, wala pa cure. It's a deadly disease and a highly communicable disease. And in his work, he used to evaluate the effectiveness of vaccination against smallpox. Nag-develop siya of model. I think gamit niya at this time is using the SEIR or the SEIR model. S stands for susceptible. I stands for infected. And R stands for recovered. So, susceptible sa disease, nga pwede pa potential nga ma-infected. If I'm infected, kato nang na-infect na siya sa virus or sa disease, and then able to transmit, na siya potential to transmit to other susceptible. And then those people put na from the infected will actually eventually recover and gain immunity from that disease. So, na siya direct resolve na niya. And also, later on it's a very long time, in 1906, taas ang gap nila. So, in 1906, Hamer formulated and analyzed a discrete time model in 1906. So, this is analytic mo siya, kanikang Bernoulli analytic. And then for Hamer, he developed a discrete time model. So, this is more on the simulation part. Okay? And he studied and understood the recurrence of measles epidemics. So, magbalik-balik. This is like the flu. You have the normal flu, that's why every year natin vaccine. And then, in 1911, Ross developed the differential equation models for malaria. Well, malaria is also one infectious disease. Okay? And actually, in his work, he won the second Nobel Prize in Medicine. Amazing. And Kermack and McKendrick later in 1926 extended the Ross models and obtained the epidemic threshold results. So, na mga threshold na yung mga important result kaya yung nakuhaan. Okay? So, for the mathematical epidemiology, so talking about the how to do about it, there are some of this one, ay mga assumptions na dapat nato i-take or i-notice, especially on the also notation. So different models will have, I think, more or less basic assumptions, but siguro lahat silang notation. But the same lang ang idea. Okay. First is the population has a constant size n. So overall sa over the course sa imong pag-model, the very simple model, the basic assumption is constant ang imong n. Well, in reality, this is not actually true because ang n mag-vary man na siya because na kay birth rate, na kay death rate, na kay migration, na kay immigration. But for a simple case lang, we'll just consider na ang n, the total population, is constant over the course sa imong epidemic or pandemic. And then the population are divided into compartments. That's why na ako as susceptible, pwede po infected, pwede po sa mga recovered, pwede po sa death, and so on. Or pwede po add kag na i-quarantine people. Okay? Another assumption is the population is homogeneously mixing. So homogeneous na siya, walay pili. Kanang anyone pwede mag-mix, walay pili ba? Random siya. Okay? The infection is transmitted primarily by person-to-person contacts. So, ano siya? One assumption. And we will ato ano siyang i-consider ginawa ito ang gamitin, person-to-person. And then, individuals recover. So, eventually, ang individual makarecover sa disease. And ma-remove siya from the infected compartment or infected class at a rate, na siya rate, okay, proportional to the number of infectives. Of course, kung dagan ang imong infectives, more or less, dagan po ang imong mga ma-recover, proportional siya. So, ano siya, have the infected, and then they recover. So, multiply ang iyang relationship. Okay. And na siya proportionality constant, what we call the recovery rate. In this case, we'll be using gamma for the recovery rate. Also, in this case, para ma-simplify ang mga problem, we ignore demography, such as birth and deaths, and so on. So, three of the most popular models ginagamit in mathematical epidemiology are the SIS, the SIR, and the SEIR model. Actually, naapa ni uban, have the SEIR and other models, mga modifications here. But for now, let's just focus our attention on this. For the SIS model, we have S stands for susceptible, I for infected, and nganong balik siyang S because mo siya mahitabo. We have the susceptible population, and in this susceptible population, na siya tendency or potential to become infected or to become infective later on. So, muna siya dali. So, na siya rate na mahimo siyang infected. Okay? And then later on, yung mga infected, mo recover man na siya. But since mo recover siya, mabalik siya sa S, meaning, dili siya immune. So, once na maka-recover ang mga infected from the disease, it doesn't guarantee or offer immunity. So, he or she or that person again will become susceptible. Then, pwede siya ma-infect na sa balik and so on. So, sa cycle na sila. Whereas, so, depende siya sa unsa nga type of disease. There could be some disease or particular disease ginana ang iyang scenario wherein from susceptible ma-infected ka, and then if you recover from that disease, you will not gain immunity from it. Tapos pwede pa ka ma-reinfect, so you go back to the susceptible compartment. Then we have the SEIR, so SIR model. From the susceptible, you become infected or infected, and then from the infected, you can gain actually immunity. Okay, you recover man. Okay, naakadali nga compartment na. You recover from the disease. You don't go back sa susceptible na compartment because you gain immunity. So you are removed. Pwede po na siya remove. You are removed from the susceptible and the infected compartment. So there are two cases nga napiuban kay duha ka case ma-remove siya. It could be naka-gain siya immunity or through death. Okay. In this case, immunity. Kung ma-remove ka from the death, lahat na po na siya nga model. We have the death and the SIRD. This becomes SEIR. Okay. Then we have the SEIR model. So specific na siya nga klase nga model for a specific type of virus or disease. So we have from the susceptible compartment, dili automatically mahimong infective ang person once na ma-contract niya ang iyang virus because naman siya exposure time. So, once na ma-expose ang imuhang individual from the susceptible compartment, naa siya window until such time nga mushow siya og symptom and that person will become infective individual. Specific case ani nga disease, we have the SARS. Way back in, I forgot the date. I think that was in 2003 ang SARS. So ang SARS is maka-infect lang ka if you become infective if mushow ka og symptom after exposure. Usually after ka ma-expose around 1 week, mushow kag symptom, nag-ubo ka, naghilanat, isut ka ginhawa. That's the time you become infective. Unlike coronavirus na once na ma-expose ka, you become infected automatically even though wala pa kay symptom. Okay? So, medyo lisod that's why lisod kay ang coronavirus. Okay? Even though wala pa kay symptom, wag juga kahibaw if na-infected ba ka or wa. So, pwede na ka maka-infect. Okay? Nanakadali na compartment. So, that's why sa coronavirus, importante kayo ang contact tracing. Naaba ka sa lugar or naaba ka sa certain group of people nga na coronavirus na nga disease, so you are actually exposed. Okay. Muna siya nila. So this is for the SEIR model. E for the exposed. So let's focus now on our attention on the SIR model lang sa. So because this is one of the simplest. But actually captures na ang iyang characteristic or dynamics of how the disease is spread. So from the susceptible compartment, the transmission of the disease is by person to person, and the transmission rate is given by beta. So naa siya is probability or transition rate na ang imong susceptible will be moved from the S to the I compartment. And from the I compartment, na po siya transition rate of recovery rate of gamma. Okay? Meaning that person is that person recovered and gained immunity from the disease. So, muna to ang mga notation. S stands for susceptible to the disease. I is for infected individuals who in turn can infect others. And R would be your recovered individuals who gain immunity from the disease. And if you sum all these variables, the susceptible, infectives, and the recovered people, the individual, that should total to a constant and the total population, which, if we recall, this is one of our assumptions that we have a constant population over the course of the pandemic. And beta is your infection rate, and gamma is your recovery rate. So we can put this into abstract form. So we have this description of our model. So we can now do mathematical modeling on this. Okay. So it is determined by this equation. It is a set of differential equations. Take a look at this. So this might be intimidating to look at first, but believe me, this is easy rin gid siya mga sets of equation if you understand what's going on underneath behind the curtain. So what we are looking at on any mathematical model is we look at the change. Diha man ta makakuha information, right? Unsa kahay we want to look at the time evolution of a certain variable. Let's say unsa kay time evolution sa mga susceptible, unsa kay dynamic changes sa imong infectives and recovery or the recovered individual. Now, based on this equation, the change of the susceptible with respect to time is equal to this. Here. So, ang infective, the susceptible, mo interact siya sa imong infective. This is the total population with this particular rate. At a certain rate. Okay? So, of course, naakay mamainusan ang imuhang number of susceptible because mapadulong mo siya sa infective. Kaya ma-infect man siya. And ang iyang interaction is based on this one. Kung unsa na siya kadako. O kung unsa pod kadako ang imuhang susceptible. Right? Okay, multiply mo na siya. And this is a minus sign because makuhaan man yung imuhang S over time. Makuhaan siya because those susceptible will become infected. Okay? So, minusan siya. This is a number. And then, katong mga na-minusan sa susceptible, of course, those people or individuals will become infected. So, ma-plus na siya diri. Okay? So, ma-plus na siya. Muna siya ang number of infective or infected individual over time. So, derivative na siya with respect to time. But, ang mga infected, mamainusan po na siya on the number of people na maka-recover. Right? Given by this recovery rate. So, katong mga number of people, individual na maka-recover, mo-add po siya sa imong recovered individual. Right? That's why, if you add mo na siya, ds over dt ay plus di over dt plus dr over dt. Diba this is s plus I plus r plus n, or that's the derivative of n with respect to t. Now, since we are assuming na ang n is constant, it actually simplifies the problem. So 0 na siya, constant. Now if you add this one, this is where ds is given by that, di is given by this, dr is given by that. You must i-add, this cancels out, this one also cancels, so we are left with 0. Okay? Sakto na ito ang model. Or, in some other cases, in some other papers, instead na kanilang gamiton, instead na number of individuals, we can just talk about proportion of population. So instead of individuals or proportion, by having this notation, change of variable. So instead not number of individual, you can just have number of individual divided by the total population. That will give you the proportion of individuals, proportion of susceptible, right? Or susceptible fraction of infected fraction, and then have recovered fraction. Okay. So, tara, mugawas na kaano nga equation, right? So, mawala na siyang big N because we replace it with these variables, and we can just simply talk about fractions here, or proportion. So, for our case, kanya itong gamiton, kanina fraction or proportion. Okay? So, over time, tara, derivative na siya. So, this equation must have a solution. So, unsay dapat S niya, unsay dapat I, unsay dapat R. Okay? So, we can solve this analytically. You can do it sa inyong respective home at your own convenient time. During your free time, pwede nyo paon ang kanisaya solution using analytic. Ang closed form niya. But in our case, masayo na siya i-solve if you can just do discrete time model. Ito siyang i-solve using numerical methods, numerical means. Masayo siya. Okay? So to understand this problem, we'll have an example. Sa example 1, let's say ang initial value sa imuhang infected, initial infected mo is 0.001. That would mean 1% of the population. Oh, it's 0.1 actually. 0.1% of the population are infected initially. So that's actually a big amount of number, right? So 0.1% are infected. Oh, sorry. So that would mean sa 1,000 na population, ay imong initial infected kay isa. So na usa nga na-infect. Okay? And then, of course, ang imong imong susceptible is nakuhaan na mag-usa. So, kay infected man siya 0.1% kay infected. So the remaining would be susceptible na to the disease. Where R or the recovered individual is still 0, wala pa na naka-recover, wala pa na infected pa man siya sa sugod, right? Isa ka buong, or the 0.1%. And then we assume these parameter values. This is for the infection rate, and this is for the recovery rate of 0.1. Okay? So we have to do ato siyang i-program ni siya. Okay? Ito siyang i-analyze. If we go back sa itong equations, right, if you want to solve this using numerical means, one way to do it is may klase-klase ng mga method para makasolve ka sa differential equation. You can do Runge-Kutta, Euler method, and so on. But for our case, pwede tayo magamit of Euler, masayon siya, but it will give you quite good result na. Okay? So for this case, ato siyang i-discretize using Euler's method. So instead na ds, we can just talk about change, right? Change sa s with respect to negative beta si. And then change sa s, pwede siya gamitin na s of, say, t i plus 1. Right? minus S of T sub I equals negative beta S of T sub I. I of T sub I. In fact, not to confuse with this, with I, with sa kaning I. I is for infective ni siya, kani is a dummy variable. So, eventually we have S T sub I plus 1 equals S of T sub I minus beta S of T sub I times I of T sub I. Okay, we have this equation for S. And we can do the same process to get the infective and then the recovery. So we can solve this now using numerical means, using our computer. Okay, this is initial values. I equals 0. T sub 0 na siya, this become T sub 1, and so on. So ipara na ito na siya. So let's make use of that. Let's open a MATLAB code para okay. So actually nagbuhat na ko og code daan lately. Close. So take a look at this. So I made a program para maka-generate og plot sa kato nga example. So now buhat ko function. Now I have my function here, SEIR, which accepts input. Okay? Input, we have S naught, meaning katong initial susceptible population, and then initial infected individual, initial recovered individual, and then the infection rate. This is for the recovery rate. And ang time, kung unsa ang length of time na i-run mo ang mga program, could be 100 days, 1,000, could be anything. Arbitrary. So I have this function, calc, yang i-call ang mga function na calculate na kung i-define sa ubos to ra. The same input na siya. And then ang result, of course, yang i-calculate unsa ang values sa S, different values sa S at S equals 0 up to arbitrary time T. Also for the infective and then the R. So solution na siya sa pag-evolve sa imuhang S, I, and R. Kani nga equation. Right? Kani nga equation. So, i-store niya sa SEIR, and then i-plot niya using my function plot SEIR. And I also want to plot okay, later na lang isa. I want to plot the superimposed na graph of the SEIR, and I also want to plot just the infective behavior sa infections over time. I have this. So, take a look at this code here. Okay. Mao man siya ato equation, di ba, sa S, o discretize, where I runs from 1 up to T. Okay? 1 up to T, you say the total time T. So, nag-define ko daan ang S of 1, that will be my initial value is S naught. Depending on my S naught, the input diha could be 0.999, and I naught is 0.001, R naught is 0, beta is 0.3, gamma is 0.1, and T is could be 100. So this is the same equation that we had kanina, right? Balik ta din dito. Tara. Nawala akong. Okay. So kani siya nga equation. Tara. Convert this to discretized model. We have ds, we have S of T plus 1 equals S of Ti, and then minus beta S of Ti of T. So that's why na ako kaning first equation. Second equation for the infected, and then the third equation for the recovery or recovered individual. Okay? And before look na ako na siya because I want to get the values of S, I, and R starting from time 0 up to time t. Then, ako siyang gi-plot. You can explore on this. So, if pwede na siya i-copy, gini sa inyong copy-paste lang na siya, i-copy sa you copy this code and you run it in your own PC or laptop. Okay? And try to understand and analyze this code. Anong mahatag na siya? Sensible result. Let's run this program. So I have a function here, SEIR. So SEIR. And then my S naught, itong given na kanina is 0.999. And then my infective is 0.001. And my beta is 0.3. Gamma is 0.1. And T is 100. If you run this one, save akong kulang akong argument. So we have S, I naught, kulang patag R. R is 0. Okay, R naught. You run that one. So this would be my result, right? So take a look at the graph. Now, the behavior sa imuhang susceptible, infective for the red, blue for the cyan, for the recovered. Over time, mo ni mahitabo. Starting from time 0 up to 100 days. Okay, so starting from this one. So given siya ang kataimuhang initial condition, kato siya, initial condition for the susceptible, infected, and recovered, and also for the infection rate and the recovery rate. One yung behavior. If you look at this, there's really an epidemic or pandemic going on. Right? Starting from 0, from one infected individual, it rises up to tanawa. Almost 30% of the population becomes infected. That's scary. So if this behavior happens in an imong graph, then we can really say that there is a pandemic. So pandemic infectious disease na proliferate sa society. And take a look at the graph. Take a look at the infected. Here, infectives in the SEIR model. So, mo peak siya around 50 days from its inception. And then, having more or less 30% of the population becomes infected with that disease. And later on, it will die out. Inani po actually ang behavior, mahitabo sa imuhang sa tuwang case, we have the coronavirus. So, now, for this case, mas simple lang siya, right? But we just don't know kung saan hitabo sa coronavirus. It could be, naghan siya o peak ba? It could be multiple waves. This is the first wave, could be na siya, second wave dihan, so on. So, just cross our fingers, hope and pray that dili ka na ang mahitabo. So, let's go back. So you notice nga calculation is very easy. Dali education if you do numerical means, right? Given this initial condition, we have this, right? So again, as I've said, based on our model, it predicts that there is an epidemic going on. So let's take a look at another example. The same initial conditions, but this time around, ang imong infection rate, if you look at the infection rate, is reduced by a factor of 4. Okay. So what will happen? So mas hina yung infection rate, and we'll see what will happen to our prediction, to our model. Okay. Spoiler. So try to run this one. The same initial condition, but this time ang imong infection rate reduced by a factor of 4. If you run that one, oops, we get this. Okay. So if you see this behavior, let's look at the infected. We see this behavior starting from 0.001, 0.1% infected, wala siya nisaka, right? Over time, nahaw na siya. So, this signifies nga ang imuhang epidemic will die out. So, when will die out siya, that would mean walay epidemic because the disease dies out. So, that's a good thing. Right? So, and the only way to do that is to saan na siya pag-reduce ang infection rate. Kaya siya infection rate, hindi mo na siya musulod, di ba? Sa imong interaction between BS over DT. Ang beta, this one, the infection rate, musulod na siya sa imong interaction between the susceptible and the infected. So how pwede ta para mo gamay na siya nga value, we have to do something about it. That's why para ma-reduce na siya, that's why we have quarantine measures that will reduce drastically the number of infections per day. Social distancing. Then we can also do vaccination. Or we have herd immunity. I don't know if you have already heard about the herd immunity. You can search it on the net now. How does herd immunity work? Okay. So that's how it works. Can you see it? Atong i-change ng is can you see it? Ang kaning beta. Okay. If we compare, there are actually two results at ang model. So ang ginagamit sa literature is actually the R. R signifies the reproduction number. Okay, production number. R is given by the infection rate over the recovery rate, gamma. Okay. So for this case, we have 0.3 divided by 0.1, then we have 3. Sa kani, R is 0.3 over 4 divided by 0.1, we have 0.75. So clearly, we can say that there is an epidemic going on if R is 3, and there's no epidemic or the disease dies out if R is 0.75, or in general terms, if R is greater than 1, naka-epidemic. If R is less than 1, no epidemic. Okay. If you look at 3 is a very huge number. If you look at the data sa coronavirus, R is around 2 point something, 2.ish, 2.2. So, epidemic din siya. Most spread gid ang imong disease. Okay? Basta kadako ang imong R or reproduction number, R is given by this. Okay? So the idea is we want to reduce this one to less than 1 or equal to 1 para mo die out imong disease. How do we do that? Well, so I've said kanina, we do the following. Check na siya. In that way, we can stop this disease, or the disease will die out. Now, we are interested in the COVID-19 and we want to apply it in the Philippine setting. Or maybe we can narrow this down to just our own province, Cebu. Or just, Cebu province. Okay. Cebu province, or maybe region 7, the Central Visayas. Okay? We can use the SEIR model, similar man siya sa SEIR. Duha ng kabuk ang iyang branch from the eye. Instead of the recovered, itong mo gain ng immunity, we can also take into account those individual nga namatay, because those are removed from the population of the susceptible. Di na sila pwede mabalik sa susceptible because they either gain immunity, recovered, or they are dead. Wala na sila. Wala sila yung way para maka-infect. And the sets of equation that describes this third model is given by this. Take a look. Somehow similar siya. Kanina man ang na-add, right? The recovery. And the death. Na-add the death. So, Ganina, ang sa SEIR is beta gamma man to siya. Karon is alpha beta gamma. This one for the infection, for the recovery, and then for the death rate. It is interesting to study. Ato na siyang i-apply sa Region 7 na setting. I will do forecasting. We will be using real data from the Region 7, and I will be using SEIR model to do forecasting sa the number of infectives, number of death, number of recovery, and susceptible in Region 7 using Region 7 pod na data. Okay? So this will be your problem set. So I will do a separate video on this. I will discuss the natures of problem, and then kung say mga given, could be given ang data. Then we will be using one paper para to as your reference, and then we'll make use of this model. Okay? So that could be interesting. So sa next na siya nga, next separate video, I will discuss on your problem set, and then we will be working on real data and do real data science na stuff. So that will be exciting. See you next time. Stay safe and God bless.